Okay, in today's class we'll be talking something important. Well, as a matter of fact, everything that we are talking related to noise is important. Now, this topic is going to have an impact in the forthcoming topics. Now, today's topic is superposition of noises. So we are going to superpose noises and we are going to see whether superposition of power applies in the case of superposing noises. Now, before actually jumping into the topic, let us just start with a brief recap to the concept of Fourier series. Now, let me just write, let V of t be a deterministic periodic signal. Now, in this case, I can simply write V of t like this. So V of t is equal to A naught plus summation k running from 1 to infinity an cos 2 pi k f naught times t, excuse me, plus bk sine 2 pi k f naught t. Let me just make the correction over here. It is ak cos 2 pi k f naught t. Now, we very well know this is nothing but the Fourier series expansion of a simple periodic signal, which is deterministic. Now, consider this combination or superposition of terms. This is nothing but linear superposition of spectral components pertaining to V of t. Now, just like how we have seen the linear superposition of spectral components pertaining to noise, now this combination or this summation over here is simply nothing but linear position of spectral components corresponding to V of t. Alright, so let me just put it in other way around. If you combine infinite number of spectral components pertaining to V of t, now this infinite sum is going to give rise to the periodic signal, which happens to be deterministic also V of t. Alright, so what we are going to check now is V of t is a combination of infinite number of spectral components, where each spectral component is nothing but a deterministic signal. So, power with respect to signal V is nothing but the overall power associated with summation of these infinite spectral components. Now, we are going to check whether PV is equal to the sum of powers of these individual spectral components or not. Or in other words, we are simply going to check whether principle of superposition with respect to power applies in the case of a deterministic periodic signal. Excuse me. Okay, so now we already know from Fourier series, we already know this. PV is equal to A naught square plus summation k running from 1 to infinity, and I have ak square plus bk square divided by 2. Now let this be equation 2. Now if you just concentrate on this particular term, this is nothing but linear superposition of powers with respect to each spectral component of V of t. So if you just simply, for the time being, forget about the presence of A naught square, the overall power or the power with respect to the signal V of t is simply nothing but the powers associated, or it is the summation of the powers associated with each and every spectral component that exists in V of t. So I can simply conclude from equations 1 and 2, it can be said that superposition of power applies in the case of a deterministic periodic signal that is expressed as a linear superposition of spectral components. This is it. Now let's consider random noise n of t, and we very well know that this is represented using this particular equation, summation k running from 1 to infinity a k cos 2 pi k delta ft plus bk sine 2 pi k delta ft. So we know this, and just like in the previous case, this entire thing is nothing but linear superposition linear superposition of noise spectral components. So this is what we have, and in one of the previous lectures we arrived at a conclusion that the total power with respect to the random process n is simply given by twice of integral running from 0 to infinity the power spectral density associated with the noise n of t df. So we already had proved this particular formula where Pn, total power associated with n of t, and this Gn of f is the power spectral density of n of t. So this is what we have. Now let me just slightly manipulate equation 4. I can write this as twice of summation, 1 second, twice of limit delta f tending to 0. I have summation k running from 1 to infinity Gn k delta f times delta f, where this is PSD with respect to the spectral component nk of t. And we also know what a delta f is. So if I take 2 inside the summation, then I'm going to have summation running from 1 to infinity twice Gn k delta f times delta f, but this is equal to summation k running from 1 to infinity pk, where pk is the power associated with spectral component nk of t. So this is what we have. So finally the power associated with the random process n of t is simply equal to limit delta f tending to 0 summation k running from 1 to infinity pk. Okay, so from equation 5, let this be equation 5. From equation 5 we can simply conclude that superposition of power applies even in the case of random process. The only difference between this power equation with respect to a deterministic signal and the random process, as you can simply see from equation 2 and equation 5 over here, the basic difference that you can observe is over there, or the most important difference that you can observe is over there was nothing like any limit, but over here we have limit delta f tending to 0, but that is not anything to worry about. So I can simply say that from equations 3 and 5 it can be said that superposition of power applies even in the case of a noise random process. Now, one very important point which I would like to make is the reason for the superposition of power to exist both in the case of a periodic signal and a random process is the orthogonality or orthonormality that exists between cos and sine functions. So let me just write down over here the reason for superposition of power being applicable for both deterministic and a random process is the orthonormality property of cos and sine functions. So this is the basic reason. Now moving on, let's consider two stationary random processes n1 of t and n2 of t, both having 0 mean. Consider now the superposition of n1 of t and n2 of t. Now let n12 of t be equal to n1 of t plus n2 of t. Now let me call this as equation 6. Now let us see whether superposition of power applies with respect to equation 6 or not. Now we very well know that power of a random process n12 of t is equal to time average of statistical average of that particular random process. Okay, since the random process n1 of t is not deterministic, as the name itself indicates, we have the time average of the statistical average of square of n12 of t. Had n12 of t been deterministic, we would have simply eliminated this expectation or statistical average. Now let me just write this one down clearly. n12 of t. Alright then. Now let me just elaborate. This is going to be limit t tending to infinity 1 by t integral over t expectation of n12 square, just a second, this is n1 square of t plus n2 square of t plus 2 n1 of t times n2 of t dt. Now let me just further proceed. Limit t tends to infinity, 1 by t integral over t. Now expectation of n1 square of t plus expectation of n2 square of t plus expectation of, or I can write it like twice of expectation of n1 times n2 of t dt. Now I can further write this down like this: n1 square of t bar plus n2 square of t bar plus limit t tends to infinity, 1 by t integral over t, let me get 2 outside, twice of expectation of n1 of t times n2 of t dt. It should be very clear to you why these two terms, n1 square bar of t and n2 square bar of t, are not dependent upon time, is because both of them are stationary random processes. So I can further write this equation in this way: power associated with the random process n1 plus power associated with random process n2 plus twice limit t tending to infinity integral 1 by t integral over t expectation of n1 of t times n2 of t dt. So this is what we have. Now this is going to be equation 7. So let me just write it down like this: power with respect to the random process n12 is equal to power with respect to n1 plus power with respect to n2 plus twice of limit t tending to infinity 1 by t integral over t expectation of n1 of t times n2 of t. Now it is obvious from this particular equation 7, let me just call this as equation 7. For superposition of power to be applicable to Pn12, the statistical average of n1 of t times n2 of t is supposed to be equal to 0. So if this happens, then Pn12 of t will simply be equal to, or the overall power will be equal to the sum of the individual powers. Excuse me. So what is the meaning of this exactly? We can simply put it like this: if n1 of t and n2 of t are orthogonal random processes, then superposition of power applies since n1 bar of t is equal to n2 bar of t equal to 0, it can be further said that if n1 of t and n2 of t are uncorrelated, then superposition of power applies between them. So this is the basic condition for superposition of power to apply between any two given or any given set of random processes, that both the random processes are supposed to be orthogonal to each other. And this is the case usually when we deal with noise that exists in resistors, which is nothing but thermal noise. So let us suppose that n1 of t and n2 of t are thermal noises coming out of two different resistors. In such case, n1 of t and n2 of t will be orthogonal as well as they'll be having zero mean, or in simple words, thermal noise coming out of two different resistors is simply uncorrelated. Now the surprising element is the noises coming out of each of the resistors, they belong to the same frequency band, but still they are going to be uncorrelated. Now the last point that I would like to add is this equation applies. So let me call this as equation 8. Equation 8 applies when there is overlap of power spectral densities of n1 of t and n2 of t either partially or to a complete extent. So this is what we have. So this is the concept of superposition of noises.